Welcome back. So this is going to be a really fun lecture. We are going to talk about how we can start to solve one of the hardest problems in computational science, the problem of turbulence modeling or turbulence closure modeling, using modern techniques in deep learning or deep neural networks. Okay, so I'm going to jump right in. Direct numerical simulation of the fluid flow equations, the Navier Stokes equations, is a pretty powerful tool, and with Moore's law, with faster and faster computers, we're able to do really remarkable things. So this is a simulation that took 35 million CPU hours, and this is a segment of a wing, so just a small piece of a wing. And this is the full direct numerical simulation of the Navier Stokes equations. Absolutely stunning detail at all spatial and temporal scales of what's happening in this unsteady turbulent flow over a wing. So this is what we want to do. This is like the holy grail, is to model all of the scales in space and time. But we know that for real engineering flows of interest, we're unable to do that. And so what we need to do is approximate how these turbulent fluctuations that we don't want to model or we can't afford to model, how they affect the big average quantities of interest, like what's the lift and the drag, and where is the separation point going to happen on this airfoil, okay? And so that's the problem of closure modeling in general, is that even with Moore's law of exponentially growing computer power, it will take forever, 100 years or more to be able to simulate these flows we really care about at full scale, fast enough for them to be useful for real-time control, for optimization and design, okay? And so that's where turbulence modeling comes in. We want to form models of the turbulence so we don't have to simulate all of those turbulence scales. And this field is rapidly advancing. Every year there are breakthrough results in turbulence modeling now using deep learning and machine learning. So I'm going to walk you through just a few key pieces of work to get you excited about what's happening in the field and how you might be able to jump in and contribute. So there is a fantastic review paper that was written, I believe, in 2019 by Durasamy, Yacarino, and Shao, all three of whom are expert turbulence modelers themselves and who have made key advances to this field of turbulence modeling with machine learning with neural networks. And there's a lot of really, really good papers on this. Now, turbulence modeling, you can break up into a couple of key kind of groupings. There's Rand's equations, or the Reynolds average Navier Stokes, which essentially tries to model average quantities of your flow, the mean lift, the mean drag, things like that. And then large eddy simulations, which are more expensive and higher fidelity. They're trying to get these unsteady kind of movies or simulations of your flow, but on a coarser grid than you could, you can't simulate all scales, so you're going to coarsen your grid and simulate the big scales. And so we're going to jump into how neural networks and machine learning are being used in these kind of two big categories. We talked about this a little bit in the review paper we wrote, myself, Bernd Nowak, and Petros Koumatsakis, the following year, also an annual review of fluid mechanics. So kind of both of those have some references of interest. Okay, I'm going to just give you a very, very brief recap of the Reynolds average Navier Stokes equations. The whole idea, the big idea here, is that you have your Navier Stokes equations, in this case the incompressible Navier Stokes equations. Those are essentially representing conservation of mass and momentum, so mass conservation, momentum conservation. And you take your flow field of interest, your velocity field, u, which is a function of space and time, and you're going to split it into an average component, u bar. This does not vary in time. It's just your mean flow. And all of the turbulent fluctuations, u prime, all of the little stuff that's happening in time. And if you take this Reynolds decomposition and plug it into your Navier Stokes equations, you can get some kind of bulk equations for the mean flow variables, for these barred u-bar variables. But those bulk equations always have these pesky terms called the Reynolds stresses, which depend on those turbulent fluctuations, which we would rather not model. We would rather not simulate those. We want to just account for their effect on the big scales in u-bar. And so the whole closure problem, as far as RANS is concerned, is trying to, it's this issue that the mean flow depends on those turbulent fluctuations. So we're essentially going to try to model those turbulent fluctuations in terms of mean flow variables. And this is by construction, by necessity, that is an approximation. These Reynolds stresses depend on small turbulent scales that we don't want to resolve. And so we're going to approximate these in terms of larger bulk variables that we do want to model and to measure. Okay, and so that's the closure problem for RANS. Similarly, the closure problem for large eddy simulations, and this is again proposed by Smagorinsky in 1963, is that we have some high Reynolds number, very, very complicated turbulent flow. What we're going to do is we're going to try to simulate it on a coarser grid. So instead of all of this resolution, which would be very expensive to simulate, we're going to simulate these unsteady time-evolving Navier Stokes equations on this coarser grid by low-pass filtering the equations up here, and then trying to understand what happens in these kind of very, very small scales, smaller than these boxes, what's happening inside these coarse boxes. We're going to model how those affect the physics. And so essentially the entire LES closure problem amounts to the fact that there is nonlinear coupling between the small scales and the big scales through convection. And that nonlinearity makes it so that we need to take into account the tiniest scales even when we simulate this kind of coarse resolution simulation here. And so this is called sub-grid scale modeling, or SGS models, where I need a little model for every single one of these coarse boxes of what's happening under the hood, what the little turbulent fluctuations are doing to these large-scale Navier Stokes equations. Okay, those are the kind of big RANS and LES turbulence problems. Now we're going to jump in, to some specific examples. And again, this idea of being able to throw away the small scales, the idea is that those really fast turbulent fluctuations typically happen on small spatial scales. They're really small vortices that are interacting. And the smallest scales in turbulence often act to dissipate energy, much like viscous diffusion in the regular Navier Stokes equations. So essentially what we're going to do is chop off these really high frequency or small scale terms and just approximate those as if they were an effective viscosity. That's called an effective viscosity model or an eddy viscosity model. And we can use that for RANS and for LES. Okay, so in RANS, again, our closure problem, one of my absolute favorite papers that uses deep learning to start to solve these RANS closure modeling problems is this paper by Julia Ling, Andrew Kurzowski, and Jeremy Templeton. So let me just go back here to this RANS equation. There are lots of approximations for these Reynolds stresses in terms of bulk quantities in the flow. These eddy viscosity models. There is the Prandtl mixing length hypothesis. There are K epsilon 2 equation models, K omega models. There's the Spilart-Alsbaran models. All of them have kind of known deficiencies for certain classes of separated flows. And so this paper by Ling et al. Uses neural networks to get better models for how those Reynolds stresses depend on the large scale mean flow structures. And one of the things I love about this paper is that they went back to the literature, back to 1975 to this, and this is the architecture they use. So they're gonna use this custom architecture that is designed to be physical. I'll tell you about this in a little bit. But they went back to the literature from 1975, before we had these supercomputers and deep learning, anything. So there's this great paper by Pope, 1975, where essentially he develops a better eddy viscosity model or effective viscosity hypothesis. And I want to walk you through this because this is going to help you understand why Ling et al.'s work is so interesting and so relevant. Because what they do, they don't just build a deep neural network end to end. They build a custom neural network that incorporates some of these better effective viscosity hypothesis modeling into it. So they went back to 1975, figured out what these models have to have, like what structure they have to have, and built that into their deep learning approach. Okay, I'm not going to read every word, but I just want to walk through this very briefly. This is the Pope paper. Okay, so we've already talked about this in the last video. So the first effective viscosity hypothesis was Boussinesq 1877, which basically says these turbulent Reynolds stresses can be modeled as some effective viscosity times things that depend on the bulk flow, kind of these averaged barred quantities, U bar. And here subscript 1, 2 means partial big U, partial Y, I believe plus partial big V, partial X. Okay, something like that. Good, so the Boussinesq hypothesis fails for boundary layers over curved surfaces. And so there's things you can do to fix that. Okay, and this is basically the generalized Boussinesq hypothesis for 3-component flow. Good, and then the approach taken in this Pope paper is built on this work by Lumley, 1970. And Lumley is one of the giants of reduced order modeling, POD, proper orthogonal decomposition, coherent structure modeling. A lot of my work, 50 years later, is built on the stuff that Lumley did in the 70s. But I just love this paragraph. I wanted to bring this up to you. So this is based on Lumley 1970, but let's read this last sentence. In forming the tensor polynomial, Lumley 1970 made illicit use of the alternating tensor density, and so the result and some of the conclusions based upon it were incorrect. Illicit. So Lumley was into like Breaking Bad type turbulence modeling here. He made illicit use of the alternating tensor density. And that's one of the things that Pope is going to fix in this paper. Okay? So the Pope paper, again, we're going to bring this back to deep learning. This is going to guide how we build our neural network, or how Ling et al. Built their neural network. So just like these K epsilon 2 equation turbulence models I told you about, where K is the turbulent kinetic energy and epsilon is the rate of dissipation of the turbulent kinetic energy, that's the K and epsilon here. You can essentially use those to get these 3 quantities of interest here. A are these kind of normalized Reynolds stresses, and S and omega are these symmetric and anti-symmetric tensors that essentially will help us to model this A quantity that we want to model. We want to model A just in terms of these bulk flow quantities, big U's. Okay, good. And so mathematically, after a decent bit of math, what we find is that there are 10 tensors and 5 invariants, or 5 conserved quantities, that pop out of this modeling framework. And so these are the 10 tensors that depend on that S and that W that we're trying to model. And these are the 5 invariants that have to be invariant for any turbulent closure model that is built on this theory. And so the long story short, you can model your Reynolds stresses in A. This is the thing we want to model in terms of those bulk quantities, in terms of a sum of those 10 tensors in big T, these 10 tensors here that you can compute. And so this is where Ling et al., you fast forward almost 50 years, 45 years, I guess 40, this paper is 2016, Ling et al. Fast forward 40 years, and we are going to find what combination of these tensors T add up to form the Reynolds stresses using a deep neural network. Okay, so that's really the name of the game. There's this really rigorous mathematical justification for why a general RANS model should take this form, where there are 10 kind of basis tensors that you're going to add up in a special combination to get your Reynolds stresses. And this might vary in space and in time, depending on different properties of the bulk flow. And so what Ling et al. Did was essentially model, and I want to go back to that neural network picture. They essentially, instead of just building a big deep neural network, which is what you might have done if you were naive, they built this custom physics-informed neural network structure that has an invariant input layer and this kind of tensor layer times these coefficients, so that by construction, the network that they have designed, the turbulence model that pops out satisfies those 5 invariants. It's Galilean invariant. It satisfies the basic physics that has to be satisfied for a valid RANS model. And so I love it because they have actually built in the physics by looking back 40 years to a really seminal paper by Pope. And so if you look at their results, you find it's a little hard to see. I think this is a pretty high resolution picture. So if you zoom in, you can see this. This is basically flow over a dip that will separate. So there's going to be separated flow. So here's the true direct numerical simulation. And you see that there's this kind of separation bubble here as the flow separates and reattaches. Now we know that that's really hard for RANS models. This kind of linear effective viscosity and quadratic effective viscosity models just don't have that separation bubble. But their kind of tensor basis neural network that is this custom physics-informed neural network I showed you, if you look, it does have a small separated bubble right there. Now, it's not exactly the right size, but in principle, this gives you better predictions because we are respecting the known physics. And so this was, a paper from 2016. In the last 5 years, there's been a lot of progress. So making this kind of more production ready and bigger, better training data to train these neural networks. Okay, good. So that's one of my kind of favorite papers in the field for RANS modeling. Now, if we go to large eddy simulations, there have been some really interesting works using neural networks and deep learning for LES as well. Okay. And so I'm just going to show you a couple of these. One of my favorites is this paper by Romet Malik, Omer Sen, and their colleagues. Again, 2019 JFM, they're using deep neural networks to model what the subgrid scale physics, how that's impacting kind of these large scale Navier Stokes equations. And so they have built this kind of custom neural network, again, where they're putting in physical quantities of interest. They have a deep learning architecture, and what pops out is this term that is needed to close the subgrid scale modeling problem, this kind of pi tilde. I'm not going to tell you exactly what that means. You can go read their paper. But they get very, very nice large eddy simulation models that are closed, not by using these kind of heuristic by hand physics closure models, but by kind of a deep learned closure model. So they train it on high fidelity direct numerical simulations where they know the truth. And in principle, they can learn better closure models for how the subgrid scale physics affects these larger scales. So really cool paper. I really like this one a lot. I encourage you to read it. They're doing tons of great stuff since then. Another really interesting paper, and I talked about this in my lecture on deep reinforcement learning, is this work by Novati, Koumetsakis, and their colleagues, where essentially what they've done is used a multi-agent reinforcement learning approach to the same LES subgrid scale modeling. So here is a fluid flow simulation on a very, very fine mesh where lots of, it's resolving all of the physics. What they do is they try to massively coarsen the grid to just these blue points, and then they learn, kind of using this multi-agent reinforcement learning, they learn the interactions that would capture and resolve the physics that's happening kind of at all these red squares that are being under-resolved if you just use blue squares on a coarse grid. Very cool idea. This just came out in Nature Machine Intelligence, and they've shown, I'm showing you a couple of pictures here. They have really, really nice plots showing kind of the convergence of statistics of these simulations using this learning approach. So really interesting, kind of accurate and generalizable approach to LES with, again, deep reinforcement learning. And this just is kind of some of the pictures from their paper that I really liked, where they show kind of flow field structures. I believe the second row is the LES, kind of these large eddy simulations at a coarse resolution. And then these are the Smagorinsky coefficients below. So again, if you really want to know kind of quantitatively how well this is doing, you should go check out their paper where they have these very nice quantitative scaling plots of accuracy versus resolution and things like that. Okay, good. The last point I want to make in this discussion about how deep learning can be used for closure modeling is that a lot of this is actually very closely related to super resolution in image sciences. So what we're essentially trying to do is infer what's happening under the hood or behind the scenes of this course simulation, so that we know how these course boxes are interacting with each other, and we can resolve the effect of the fine scale physics that's inside. So underneath this course resolution, there's all of this microscale physics happening, just like underneath this course image, there are eyelashes and a cornea. How do we account for those effects, in the model? And so if we can have better super resolution algorithms, so if we can infer what the fine resolution is just from the coarse resolution and its neighbors, we can use that information in these closure models. And there's some really interesting work on this. Ben Erickson has done some great work on super resolution using neural networks. Sam Tyra and colleagues from UCLA have also done really nice work on kind of deep super resolution in fluids. And there's also a ton of work in the atmospheric and ocean sciences community. So climate science and weather scientists have some of the biggest fluid problems around, right? Their Reynolds number are Earth scale Reynolds numbers. And so they're also very interested in these LES and super resolution techniques and how they can build those into their climate models. Okay, so with that, I think I would like to conclude and just, I hope I've gotten you excited. This is one of the most important problems. If you want to do any large-scale engineering or science involving a fluid, chances are you're going to be modeling the turbulence instead of resolving all of those scales. And in the modern era, there are some really powerful emerging techniques in deep learning that are helping us do a better job of modeling the turbulence. I will point out, my personal philosophy is very much like the Ling et al. Philosophy. The more physics you can bake in, the more you can make your deep learning physical by construction, the better of a job you're going to be able to do when you use it for physical modeling. All right, thank you.